Hi, I'd like to welcome you to a quick introduction to Ocean from Spot by NetApp. Spot's continuous optimization technology gives your workloads and applications the cloud infrastructure they deserve, always scalable, always available, and always at the lowest cost possible. For containers and Kubernetes, infrastructure management is an ongoing challenge with many operational complexities. Ocean, Spot's serverless compute platform for Kubernetes, addresses key areas of container infrastructure management with real-time intelligent automation to maintain high-performing, available, and cost-efficient environments. How does Ocean do this? It integrates into any existing worker cluster that you have running inside your own control planes, whether that's EKS on AWS, GKE on Google Cloud, Kubernetes, AKS on Azure, or some sort of vanilla implementation like KubeADM, KubeSpray, OpenShift, Docker Swarm, ECS, or any other container orchestrator you can think of. Your control plane and all your configurations and management will stay in place while Ocean wraps around your data plane to continuously optimize all the worker nodes based on the real-time requirements of your pods. Ocean does this across 3 different layers. First is infrastructure provisioning and pricing. Ocean will choose the instance pricing model based on the availability of your environment. If you have any capacity reservations that are not currently utilized or commitments to the cloud provider that you're not using, Ocean will prioritize these pre-purchased instances as long as they're a good fit for your workload, eliminating unnecessary waste. Once those run out, Ocean will leverage the cloud provider's excess capacity, known as Spot instances on AWS, Spot VMs on Azure, and preemptible VMs on GCP. Those instant pricing models offer a 70 to 90% discount compared to on-demand prices, and Ocean will manage their fault tolerance to guarantee an enterprise-grade SLA and high availability, ensuring you're not experiencing any interruption to your application. Once Ocean figures out the right pricing model based on what's available in your account, it takes a container-driven approach to determine the instance type, shape, and size based on the application's specific requirements. Ocean considers container CPU and memory requests, as well as any labels, taints tolerations, affinities, and anti-affinities, persistent volumes, and any other configurations you might have, in order to understand the cluster and provision it in the most efficient way. This Tetris-like scaling model determines the right instance at the right time and bin packs containers to be as efficient as possible. Typically, this capability alone reduces the footprint of containerized clusters by 20 to 30% from the moment it connects and starts orchestrating them. This method of intelligent infrastructure provisioning and pricing the first layer of infrastructural pricing can get you a 50% to 70%, even 80% discount compared to the pricing models you're currently using, running on less infrastructure because of all the additional capabilities Ocean brings to the table. Ocean's right-sizing capabilities afford even greater efficiency by making sure your containers and microservices are actually requesting the right resources and the right amount of them. With continuous monitoring of every microservice, Ocean compares the CPU and memory requests of workloads to their actual consumption over time and gives real-time recommendations to improve resource configurations. Applying accurate resource definitions helps avoid over-provisioning and prevents unnecessary cloud costs. To do all of this, Ocean only requires one small operator inside your cluster. This connection allows Ocean to see the status of the cluster, its resources, and communicate with your control plane to make sure everything stays in order. Ocean will integrate to any infrastructure as code. You're able to deploy it from the UI, but also from Terraform, CloudFormation, Ansible, as well as many SDKs and RESTful APIs. Tools like EKS, CTL, and KOps, the open-source project for Kubernetes operations, both have native integrations into Ocean and work right out of the box. Let's quickly jump into Ocean so we can see some of what you'll work with. Integrating Ocean into any given cluster is extremely easy. So, you have an EKS cluster running today. You want to migrate your configurations to Ocean. We'll run a test cluster here, running in North Virginia. And we'll pull one of the autoscaling groups underneath to get the metadata out of it. Ocean will immediately fetch all the metadata of your current workers, your VPCs, your subnet images, security groups, keepers, user data, tags, and everything else necessary. You won't have to select the instance sizes, but you can delist a few families and limit the minimum and maximum size of them. However, Ocean will choose the optimal instance at the right time to optimize your cluster. We'll then quickly deploy the controller token or the controller pod that we've discussed in here, basically the Ocean operator. And once it's up and running, I'll press Test Connectivity. We'll skip that for now as it takes about a minute to deploy. And Ocean is good to go. You've been set up on EKS with all the optimizations I've just mentioned, and there's a Terraform ready for deployment. Let's take a quick look at what you'll be getting once you've finished that 2-minute deployment. You get a great dashboard that will immediately orchestrate and optimize your cluster, will run across a variety of instance shapes and sizes, and will leverage different life cycles, reservation spots, and on-demand. You will immediately start getting granular cost analysis on every namespace and deployment you have running in your cluster, and be able to run detailed filters around every label and annotation running inside Kubernetes. It's a great way to track costs in those multi-tenant clusters that can potentially have hundreds, if not thousands, of users deploying applications into them. With the right-sizing features mentioned earlier, all your applications will be monitored for the utilization to ensure your pods are as packed as possible. From there, you'll just get additional visibility into your clusters from namespaces and deployments underneath, and the amount of pods running over time, the labels and annotations on every single one, the pods themselves and how they're behaving, as well as the nodes and their status and what's going on inside of them. A few other things that are important to mention about Ocean is that on top of all these things, Ocean is going to provide you the ability to run multiple configurations within the same cluster whilst maintaining a single view. So imagine your data scientists want to deploy GPU workers. All you have to do is add launch specifications with a GPU-enabled AMI, and you're good to go. Ocean will pick up that those deployments require the GPU, and will know to go back to that underlying specification. Additionally, there's no need to manage over-provisioning of clusters or scale-ups. Ocean does all of that for you to make sure to automatically and dynamically allocate excess resources at about 5% of the cluster capacity, which is possible for the user to change. In order to make sure that whenever there is a small scaling event, like a horizontal pod scale, pods will be instantaneously scheduled and Ocean will scale up immediately after for more headroom. If there is a bigger scaling event, Ocean will aggregate the total amount of resources from all the pending requests into a single scaling event with as many instance types, shapes, and sizes to achieve the desired result. Lastly, in order to keep clusters constantly optimized, Ocean will dynamically scale down when it sees clusters have excess resources. So, while the open-source cluster autoscaler will take any part of any node that has less than 50% utilization and will randomly scale down by terminating a random node, Ocean proactively looks for nodes that can be drained and will reschedule pods to other nodes for maximum optimization. For example, if you have 10 nodes with 10 pods each and you scale down 10 pods, the Kubernetes scheduler might take down 1 pod for each node. You'll then have 10 nodes with 9 pods, each at 90% utilization, but the cluster autoscaler won't do anything about that. The Ocean autoscaler, however, will understand that at this point, if you deregister and drain node number 10, the 9 pods on it could fit themselves on nodes 1 through 9. And then, instead of running your 10 nodes at 90% utilization, Ocean will understand it can reshuffle things a bit and get you 9 nodes at 100% utilization, reducing your cluster footprint by 10% immediately. This happens constantly and continuously in real time to get your clusters as optimized as possible. Thank you for joining us for a few minutes on Ocean. I hope this was useful. We look forward to seeing you, meeting your teams to start some deployments and saving money.